let me tell you some more details about the brand new products we had to offer. So as I mentioned earlier, the 600 series Versa is the next generation Versa, and it provides half micron spatial resolution with a 40 nanometer minimum voxel. And this is a nearly 30% improvement in our specification compared to the 500 series. The 500 series was 0.7. The 600 series is now 0.5 microns spatial resolution. The heart of the system is a high power source, a new source design. It provides up to 2 times higher throughput than the Xradia 500 series. Also, it maintains high resolution with excellent stability. By all the learning that we have gained from the 500 series has been built into this new source, and it maintains excellent stability and high resolution across the full energy and power range. Also, there's some ease of use improvements, including with the new source, it is very fast, activating very fast, and this improves the user's experience in using the tool. And like the 500 Versa, it does enable visualization of defects prior to physical failure analysis, guiding cross-section, mechanical cross-section, leading to improved FA success rate. In comparing the image quality versus the 5XX, the 6XX provides at least, if not better, image quality at up to 2 times faster acquisition rate. The example I'm showing is a reliability test. In this case, it is 30% faster than the 5XX. But in certain situations, the system goes up to 2x faster than the 5XX. This is the industry's only synchrotron-based nanoscale 3D X-ray microscope, and it delivers the highest possible resolution, 3D resolution from an X-ray instrument that is available on the market. It provides 2 modes of operation. One mode delivers 150 nanometer spatial resolution. The second mode delivers 50 nanometer spatial resolution. Similar to TEM, this instrument requires sample preparation, and it requires that a cylinder is extracted from the sample. In this case, it contains a micro bump here, and also some back end of line features, metallization features. But this sample is typically 100 microns in diameter and can be easily extracted in under 1 hour using a third-party laser sample preparation device. And one thing to point out, once the sample is prepared, the imaging is not destructive, non-invasive to the sample. And so it can be used for imaging ultra-fine pitch interconnects and other ultra-fine features, such as back end of line features, as you see on this image here, but also chip package interface type issues may be imaged with the ultra. And as I mentioned, this is a unique instrument. It's got a unique X-ray optics configuration that is similar to instruments that are used at synchrotron facilities. So it is a quite unique lab-based instrument. So to give you a feeling for a comparison, Versa versus Ultra, the Versa X-ray instrument images without requiring sample preparation, so the whole sample intact. It provides minimum half micron spatial resolution, and it is the most versatile X-ray microscope for imaging localized defects within intact packages. The Ultra does require sample preparation, typically accomplished by a laser-based lift-out preparation. the sample volume remains intact and is protected from the environment and is imaged by either 150 or 50 nanometer spatial resolution. And it is unique for analyzing ultra-fine pitch flip chip and bumped connections. So this is a typical failure analysis workflow. It starts at the left side where you've confirmed electrically that something has failed and the sample is intact at this point. Then there's some elements of physical failure analysis which begin to be destructive to the part over to the right-hand side. So where does the Versa fit? Is by imaging intact devices and looking at internal interconnects before proceeding on the FA workflow. And then the Ultra is placed more so to the right because it requires sample preparation and analysis of back-end of line and chip package interconnect problems. So here is an application example from the Ultra. On the left side is the extracted region of interest, 100 micron cylinder. And in this case, we are examining the microbump. Here's the 3D data set that is produced by the Ultra. This is a 25 micron microbump, copper pillar, and the solder in between. By taking a virtual cross-section, you can see that here is an image, and you can even see the intrametallic, and you could begin to see Kirkendall voids here in this virtual cross-section. Before, it is pretty much required to use SEM to image and actually image intermetallics. With the Ultra, you could begin to see the intermetallics as you could see here in this virtual cross-section. You can also look at just the solder by itself, and that's what this is, and you can actually look at the roughness that's at the interface. So there's some flexible analyses you may accomplish with the Ultra, and you can visualize bump alignment and bond line stack-ups, solder shapes, extrusions, interfacial textures, intermetallic thicknesses, and so on, which enables you to localize, determine root cause of buried defects, do nano-level design and process optimization, also to help you with your simulation models, particularly in development. The Context is a microCT. It enables large field of view, 3D X-ray images for a variety of sizes, flexibility in sizes like the Versa, and it provides a minimum 0.95 spatial resolution with half micron minimum voxel size with excellent image quality and contrast. It is using a high-speed 6 megapixel detector, a flat panel detector, as I described before, and it provides a large field of view with a 10x greater volume for the 3D data set as compared to the Versa XRM. The one advantage it has is you can field upgrade or field convert it to an X-ray microscope. Of course, like all microCTs, the resolution will degrade as sample sizes get bigger. So high resolution is maintained for very small samples only. As samples get bigger, the resolution degrades like all microCTs. So here's an example from the Context. This is a smartwatch, and with the Context you can image the entire smartwatch, as you see here. And to some level you can actually zoom in as well by moving the watch closer to the source. You can get a higher magnification image, as you see here. You're just limited, you can move it no closer than to allow it to go and rotate in front of the source.